Let's make sure that we're able to look at a topology and determine who's the root bridge, which ports are forwarding, and which are blocking. To begin with, we ask the question, who is the root bridge? Remember that the root bridge is going to be the switch that has the lowest bid, the lowest bridge ID. The bridge ID is made up of, there's the bridge priority, and if they're the same, the tiebreaker is the MAC address. So first, let's look at the bridge priorities. And you'll notice that both switches A and B, they have the same priority, and they're lower than the priorities on C and D. A and B have a priority of 16.384. C and D have a priority of 32.768. So we know that the root bridge is going to be either A or B. As the tiebreaker, we look to the MAC address. Which is lower, 000? That's the first three hexadecimal digits for the MAC address on switch A, or 001. Well, 000, of course, is less than 001, so we now know that switch A is our root bridge. Next, we ask, what are the root ports? Remember that a root port is a port on a non-root bridge that is closest to the root bridge in terms of cost. And unless we go in and do some manipulations with cost, the cost is going to be dependent on the interface speeds. Let's go ahead and label the costs on screen. This link between switch A and B up at the top, this is a 10 gig link. That has a cost of 2. The gig links have a cost of 4. Let's put a 4 on each of those links. Got a couple of links going between A and C. We've now identified the cost of all of our links. And on switch B, we ask which port is closest to the root? Which port is closest to switch A in terms of cost? Well, I'm going to suggest that it's TE, or 10 gig Ethernet, 1/0/1, because we only have a cost of 2 if we go out of that interface to get to switch A. If I go out of gigabit 1/0/7, it's a cost of 4 just to get down to switch C, and it's an additional 4 to get up to switch A. That's a total of 8. Same thing if I go out of gigabit 1/0/5. It's a cost of 4 to get down to switch D, and another cost of 4 to get up to switch A. That's a total of 8. It's much less costly just to use the 10 gig 1/0/1 port. That's our root port. Let's label it. This is our root port. I'll do an RP for short. What about switch D? Switch D could go directly to the root over this gig link. That would be a cost of 4. Or we could go up to switch B, which is a cost of 4, and then over to switch A. That's an additional cost of 2. So the cost would be 6 if we went via switch B, but it's only cost of 4 if we go directly to switch A. That means that gigabit 1/0/1, that's going to be our root port on switch D. Switch C is a little bit more complex. If we went via switch B, it would be a cost of 4 to go up to B, and then an additional cost of 2 to go over to A. That's a total of 6. That's going to be more costly than either of these links. I've got 2 links. They have the same cost. Which port is going to be my root port? It seems like a tie. Well, in a case like this, we go with the port that has the lowest port ID. That's our tiebreaker. And gigabit 1/0/10, that's lower than 1/0/11. 10 is less than 11, so 1/0/10, that becomes our root port. Next, we ask, what are the designated ports? A designated port exists on every segment, and it's the port on that segment that's closest to the root in terms of cost. We can start out really easy on switch A, and we see these 4 segments coming into switch A. All of those switch A ports are going to be designated ports because we don't get closer to the root than actually being on the root. So we can easily label all 4 of these as DP for designated ports. But what about our other links? We've got this link between switch C and switch B. Who's designated on that link? Well, switch B only has a cost of 2 to get over to the root. Switch C has a cost of 4 to get up to the root. So which end of this link is going to be closest to the root? It's the one on switch B. This is going to be our designated port on that link. What about this link going from D to B? Same logic. B is only a cost of 2 away from the root. D is a cost of 4 from the root. So the switch B side, that's closest, that's going to be our designated port. We've now identified the root bridge, the root ports, the designated ports, and assuming none of the ports are administratively shut down, that means the remaining ports are going to be non-designated ports. In other words, they're going to be blocking. I'll label them with a B. Gigabit 1/0/11, it's currently blocking. Gigabit 1/0/2, it's blocking. And our other port that we've not yet labeled on switch D, it's gigabit 1/0/2, it is blocking. We've now analyzed this spanning tree topology. We began by asking, who's the root bridge? And it was the switch with the lowest bridge ID. We first look to the priority, and if we have a tie as to the lowest priority, we look to the MAC address, and we go with the lowest MAC address. Once we identify the root bridge, we look to the non-root bridges and ask which port on each of these non-root bridges is closest to the root in terms of cost, and that identifies our root ports. Then we look on each segment and say which end of this segment is closest to the root in terms of cost. And whichever one of those two ports on the end of a segment is closest to the root, that becomes the designated port for that segment. And as a result, all of the ports on the root bridge, they become designated ports. And all of the remaining ports that are not root ports and they're not designated ports, as long as they're not administratively shut down, they are non-designated ports, which means they are blocking. They're standing by to forward traffic if the link connected to the root port fails.